So that's what this chapter is about, is redox reactions like that and how they can be used to generate electricity. So we need to learn how to balance redox reactions. And so we do need to review a little bit from chapter 4. Oil rig. You probably heard that in 1A. This stands for oxidation is loss of electrons. Reduction is gain of electrons. And that's another one of those couplets that's really easy to mix back and forth. You've got oxidation and reduction. You've got losing electrons and gaining electrons. And so we need some sort of a mental trick to remember which goes with which. So oil rig works really well. So that's thinking in terms of loss and gain of electrons. We can also think of it in terms of oxidation state. Oxidation is an increase in oxidation state. That's a little easier to remember. Oxidation means your oxidation state goes up. Reduction is a decrease or a reduction in the oxidation state, right? So reduction means your oxidation state goes more negative. Oxidation means it goes more positive. So if we look at this example, here we have calcium reacting with water to form calcium hydroxide and hydrogen gas. And if we look at the oxidation states of calcium, here calcium is an element, and so its oxidation state is 0. Over here, calcium is a 2+ ion, so it has a +2 oxidation state. So it went from 0 to +2. That's an increase in its oxidation state. And so that's oxidation. Let's look at it in terms of electrons. How does a calcium atom become a calcium 2+ ion? It has to lose 2 electrons. Oxidation is loss of electrons. So it lost electrons, it's oxidized. Its oxidation state went up, it's oxidized. Water has hydrogen and oxygen. Here the hydrogen has a +1 oxidation state, and over here in the product we have hydrogen gas. The elements have 0 for their oxidation state. So the hydrogen has been reduced. So when we balance redox reactions, it can be pretty complicated sometimes. Occasionally you run across an equation, like we had one in lab, I think in the green salt lab, that you're like, you just go around and around in circles. You're like, what on earth? What is wrong with this equation? Well, it's a redox equation. And redox equations have to be balanced in mass, in terms of numbers of atoms of each element, like normal, but also in terms of charge. And if you're not looking at the oxidation state, it becomes really, really tricky. And so what we do is called the half reaction method. So we take the equation and we break it into 2 half reactions. We balance those individually, and then we add them back together. Here is a review of oxidation states. I'm just going to go through this really quickly. And these rules are in order of priority. So this one takes precedence. Free elements have an oxidation state of 0. Monatomic ions have an oxidation state equal to their charge. The sum of the oxidation states of all the atoms in a compound is 0. The sum of oxidation states of atoms in a neutral molecule is 0. In a polyatomic ion, it equals the charge on the ion. So the example here is NO3 has a -1 charge. So the oxidation states of the nitrogen and the 3 oxygens have to add up to -1.
Like oxygen, like -2.
We're getting to that. In their compounds, metals have positive oxidation states. And that usually corresponds to their charges. Group 1 is always +1, group 2 is always +2. And then the nonmetals. And these are the ones that are a little bit squirrely. So in their compounds, nonmetals have oxidation states according to the table at the right. So it goes in this order: fluorine, hydrogen, oxygen, then group 7A, 6A, and 5A. So fluorine is going to be -1, pretty much always. Hydrogen's going to be +1. Oxygen's going to be -2. And then group 7A, the other guys get to be -1, -2, -3. So if there's a disagreement, like in nitrate, you've got nitrogen and oxygen, who gets to win? Whoever's higher in this list. Oxygen wants to be -2, so in nitrate, oxygen gets to be -2. Nitrogen's in group 5A, he's lower down on the priority. He has to take what's left. So go back to chapter 4 and review that if you need to. So this is the procedure for half reaction method. We're going to look at acidic solution first, and then we'll look at basic solution. So I'll go through the rules, and then we'll do examples, and hopefully it'll make more sense. The first thing is we assign oxidation states to all the atoms, and we need to identify what's being oxidized, what's being reduced. And we did stuff like that in 1A. Then we're going to separate the overall reaction into 2 half reactions, one for the oxidation, one for the reduction. We're going to balance each half reaction first with respect to mass. Balance all the elements besides hydrogen and oxygen first. Then balance oxygen by adding H2O where it's needed to balance oxygen. And then balance hydrogen by adding H+. Next, you balance with respect to charge using electrons. And so what you're going to do, when we balance an equation, the total charge on the reactants has to equal the total charge on the products. Forgot what those guys were called, the products. So just add electrons as needed. It's all in the book. It's going to be posted on OneDrive. It'll be on YouTube, and we're going to see it again in the examples. Question? I'll put it back while I'm answering Derica's question. Good teamwork there.
Is even this process kind of, because it looks really familiar, like is this what we learned in 1A, or is...
I don't think...
Because it looks like the way Dr. K showed us, but...
Yeah, Dr. K sometimes shows you stuff that isn't necessarily in the book right there. So this is probably what he showed you. I don't remember teaching this specifically in 1A, but it might have been in there. That was last fall. I have a hard time remembering what happened last week. But this is a standard procedure for half reactions.
Oh, and then we need to get this, so all those rules for assigning oxidation states and this whole process we need to have memorized by the test?
Yeah. And when you use it, you will remember it. The oxidation state thing seems trickier than it actually is. It mostly comes down to charges of ions, and then the fluorine, oxygen, hydrogen thing. So it's really not as bad as it seems. Okay. Balancing with respect to charges. And then what we're going to do is we're going to make the number of electrons in both half reactions equal. And we'll see, this will make more sense when we do it. But say one has +2 electrons in the reactants and one has +3 electrons in the products. We need them both to be the same number of electrons because we want the electrons to cancel out when we add the reactions together. So we make sure that the number of electrons is the same, and then we add them together, canceling out anything that's the same on both sides. And then double check, verify that it's balanced with respect to mass and charge. So let's do an example. And for this first one, I put the steps up here. Actually for myself, because I'm feeling a little rusty. I'll probably sound a little rusty too. So balance this redox reaction in acidic solution. So the first thing is we need to identify oxidation states. So H+, what's the oxidation state for that? +1. This is a monatomic ion. The oxidation state is its charge. How about chromium?
Elemental 0?
It's an element, it's 0. How about H2?
Element 0.
Element is 0. See, that's not so hard, is it?
Not yet.
Cr2 plus. 2 plus, it's an ion, that's its charge. So plus 2. Usually when we write oxidation states, we put the sign in front of the number. And when we write charges, we put the sign after the number. That's not something that you really have to remember, but there's a reason that I write plus 1 instead of 1
So
plus.
that's not balanced.
This is not balanced at all yet. So we're going to separate this into two half reactions now. So here we've got hydrogen going from plus 1 to 0. Is that oxidation or reduction? The oxidation state is reducing, right? It's a reduction. Now you don't have to label them, but I'm going to. So the reduction is, let's see if I can space this out. H plus going to H2. And then the oxidation is the other one. That's the chromium going to chromium 2 plus. And what I usually do, this is just my work here in the middle, I leave the state symbols out and I bring them back for the finished product. If you write them in the middle, it just gets all cluttered and it's not really necessary because that's not changing. So there's our two half reactions. The aqueous, yeah, state symbols, phases. So there's step number 2. Now we're going to balance with respect to mass. So what do we need to do to this? H plus going to H2. We just need to put a 2 in here. There's no oxygen, so we don't have to worry about it. And the oxidation half reaction, it's already balanced with respect to mass. Then we have to balance with respect to charge. So we're going to add electrons. Electrons are negative. Yes, we need 2 electrons here. See, I did not plan ahead. And we need 2 electrons over here. We have a total of plus 2 charge here and 0 on the other side. So we need to add 2 electrons so we get a total 0 here and 0 there. It doesn't have to be 0 on both sides, but the charge has to be the same. And you can only add electrons to balance the charges.
It has to be the same, so why'd you add in?
Well, because it was plus 2 here and 0.
Oh,
Those aren't the
okay.
same. Plus 2 is not equal to 0.
I was thinking the total.
And down here we have chromium. This is 0 charge and plus 2 charge. And so I'm going to add the 2 electrons over here. So that total on the right I have 0 charge and total on the left I have 0 charge. Okay? Now I'm going to look at these number of electrons. I've got 2 electrons over here and 2 electrons over there. So that is the same number of electrons. If you haven't noticed, this first example is a really easy example. And then we're going to add these together. So what I'm going to do is I've got 2 electrons here and 2 electrons there. Something that's in the reactants and the products exactly the same cancels out. Kind of like the spectator ions for net ionic equations. So those electrons go bye-bye. The electrons should always go away because you set it up so that the number of electrons in both equations was the same. So you shouldn't have electrons in your finished product. I don't remember what color I was using. So now I'm just going to add these together. So I've got 2H plus, that was aqueous, and I've got 1 chromium, a solid, and that's forming chromium ion, it's aqueous, and hydrogen, it's a gas. Whether you put the hydrogen ion first or the chromium first, it doesn't matter as long as they're on the correct side of the arrow. Any questions? Okay, we're going to do another one. So here we have copper plus nitrate ion making copper ions plus nitrogen dioxide gas. So what's the first thing we have to do? Oxidation numbers. So copper is an element, so that gets a 0. There aren't any other elements. I always like doing the easy ones first. So this Cu2 plus is going to be a +2, right? Then let's look at NO2. This is a neutral molecule, so the oxidation numbers of the 3 atoms in this molecule have to add up to 0. And so this is where we need that list. Who gets priority, oxygen or nitrogen? Oxygen does. And what does oxygen want to be? It wants to be -2, just like the oxide ion is -2. So each of these guys is -2. And there's 2 of them. So the nitrogen must be +4. And then over here, we have the same 2 guys, nitrogen and oxygen. Oxygen gets priority, so oxygen gets to be what it wants, which is -2. There are 3 oxygens. 3 times -2 is -6. We need an overall -1 charge, so what's the nitrogen? +5. Okay, so what is being oxidized?
Copper.
The copper. The copper's being oxidized because it's going up. So oxidized, I'm going to put copper to Cu2 plus. And then what's being reduced? The nitrogen. What's happening to the oxygen? Nothing. You have to have one thing being oxidized and one thing being reduced. Sometimes there's different ones going on. There's more than just that, but that's the minimum. So then down here I've got NO3 minus going to NO2. The next step is what? Nope. Mass.
Oh, mass.
Balanced by mass first. So the oxidation half reaction is done. Down here, the nitrogens are balanced, but the oxygens are not. I have 3 oxygens on the left, I have 2 on the right. So to balance that, I'm going to add water. Yes, question?
So to fix oxygens, we don't just like start trying to mess with coefficients.
No, you're not going to be able to mess. Yeah, you're not going to be able to fix it. And adding water is okay because this is an aqueous solution. There is water present. And so that's what we're going to balance it with. So we add an O over here in the water so that our oxygens are balanced. And then we fix the hydrogens last by adding hydrogen ions. See, this is acidic solution. There's hydrogen ions present. So I've got 2 H's on the right. I'm going to add 2 H's on the left. Now we do charges. So this top one, what do I need to do to balance the charge? Plus 2 electrons in the products. So I did it again. Moved it over. Okay, so on the right side, total charge is 0. On the left side, what's the total charge? +1. So how many electrons do I need? I just need 1 electron. Now what do I do? I have to get the same number of electrons. So this one has 2 electrons, this one only has 1 electron. So I'm going to multiply this whole reaction by 2. I'm going to multiply everything. I know. So that'll be 2 electrons, and this becomes 4 hydrogen ions. and 2 nitrates, and 2 NO2s, and 2 H2O.
Okay.
And then I'm going to add them together. So I have 2 electrons here and 2 electrons there. Those are going to go away. Bye-bye. See ya. Anybody else going to cancel out? No.
Nope.
So I've got copper solid plus 4 hydrogen ions plus 2 nitrate ions is going to make 2 NO2 molecules in the gas state. What's the state for water?
Liquid.
Liquid. Plus copper 2 plus aqueous.
Nice and compact.
Now, the previous one, we could have very easily balanced by inspection.
Yeah.
Can you balance this one by inspection?
No.
No, because there's no way to get the nitrogens and oxygens to come out right, because you have to throw hydrogen and water in there to make it happen.
Well, if you know all I have to do is throw hydrogen and water in there, just throw the fraction out.
Maybe. Question?
There are no electrons. Wow, there's no electrons.
Yeah, he could do it.
He would do the half reactions in his head and do it, yeah.
Yeah.
Did you have a question?
Yeah.
Okay.
I have 2 questions. I don't remember this. Oh, okay. One of them is, so like, I know on the ACS it's going to be a review of everything. If we ever run into a problem where we're finding it really difficult to try and just balance this by inspection, that's a sign that, oh, you might want to try out
Yes.
this. Okay.
Yeah, anytime, now that we know this, anytime that you find an equation that just doesn't seem possible to balance, look and see, is there oxidation and reduction occurring? Then pull it apart and do the half reactions separately. Absolutely. Mm-hmm.
And then one more, just kind of not important question. So I see that things are still aqueous, but I'm guessing we've completely left behind the realm of dealing with equilibrium problems. That just, we don't even have to deal with that.
Yeah, we are not focusing on this being in equilibrium. Yeah, and what we'll see with the electron transfer is that these are generally going to go either in the forward direction or in the reverse direction, and they're not really going to just waffle in between.
Are we going to hang out in the realm of acidic solutions, or are we going to be moving on?
Oh, we're going to talk about basic solutions next.
Oh, well, okay. As long as one or the other, but
Yeah.
not like neutral or gas or liquid.
No, you usually do these as acidic or basic.
But you can go do it all in acidic and vary and change to basic, right?
Yes, you can. Yes.
Yeah, I did that.
Yeah.
So if we can do it in acidic and basic, could we also do it in neutral solutions, or no? That's
Oh, yeah.
not.
Totally.
Well, how are you going to do this one in a neutral solution?
I don't know. I don't think I can, but can.
So, and here's a question. Are there hydrogen ions in a neutral solution?
Not free.
Yes.
Yes, there are. What's the concentration of them?
Extremely
10
small.
to the negative 7.
10 to the negative 7th molar. It's small, but there are hydrogen ions. There are also hydroxide ions present.
Everything's acidic.
So we want
And
to do
basic.
what is that?
I don't think it's going to be a problem. So let's not look for problems where there aren't any yet.
Yeah.
Okay, so here's the basic solution. There's just one extra thing to do, and that happens in step 3, where we're balancing with respect to mass. We're going to balance all the elements but hydrogen and oxygen. You're going to balance the oxygen by adding water, that's the same. You balance the hydrogen by adding H+, that's the same. And this is the different part. Neutralize the H+ by adding hydroxide ion. So you end up adding the same number of hydroxide ions to each side of the equation. So if you have 2 hydrogen ions, you're going to add 2 hydroxide ions to both sides.
Oh.
So it's not going to affect the mass balance at all.
Oh, so you do that?
What is H plus OH minus? Water.
Okay.
Okay.
And every time you do that, you always have like H plus and water on one side. So if you do that, the waters will cancel and be on the side down.
Sometimes the waters cancel, sometimes they don't.
Well, I mean, not completely, but they will.
Yeah, but you can end up with waters on both sides, and then some of them will cancel out, and it makes the canceling a little more complicated. So let's do an example. Hypochlorite ion plus this complex ion of chromium and hydroxide to give chromate ion and chloride ion. So what's the first step? Oxidation numbers, right? So let's just start on the left and go across. So here we have chlorine and oxygen. Who gets top billing? Who gets priority? Oxygen does. So the oxygen gets to be -2, then what does the chlorine have to be?
+1.
+1. Is the chlorine super happy about that?
No.
Probably not, but that's what it is. So here we go, chromium, and we've got hydroxide here, and there's 4 of them, and overall a -1 charge. Well, what's the hydrogen going to be? Well, let's think about this. This is hydroxide ion,
Yeah. Oh.
right?
Yeah.
And so in hydroxide ion, can the hydrogen be +1 and the oxygen be -2?
Yes.
Yes. And that's what they want to be. And so they're good with that. So those guys are fine right there. But then this chromium,
Oh.
+3. How did you figure that out?
What was the minus one?
But it's a minus charge overall.
So we can look at this chromium and figure out what's the charge on that chromium ion. It's got 4 hydroxides, which are each -1, and there's an overall -1 charge. So the chromium's going to be +3. And I love that you guys can just figure that out.
Oh, yeah, okay.
Okay, so chromate. Oxygen gets to be what it wants to be, -2. So that gives us a total of -8 for the oxygen. Overall a -2, so the chromium has to be +6. And then chloride ion. What's the chlorine? -1, the same as its charge. Okay, so I think this part will come back to you pretty quickly. Okay, so what's being oxidized? What's going up in oxidation number? Chromium. So let's write that guy down. We've got CrOH4 minus going to CrO4 2 minus. And then what's being reduced? The chlorine. So then we've got the hypochlorite ion going to chloride ion. So the top half reaction, the chromium is already balanced, 1 on each side, and we've got 4 oxygens on the left and 4 oxygens on the right. So the only thing that's messed up is the hydrogen. So hydrogen, there's 4 on the left, so then we're going to put 4 hydrogen ions on the right. If we were doing this in acidic solution, we would stop. But this is a basic solution. I have 4 hydrogen ions, so I'm going to add 4 hydroxide ions. I'm going to add that on the left and on the right.
Oh, that's right.
Or the right and the left, sorry. Because I'm going to combine these into 4 water molecules. So this is 4 H2Os. And now this is basic, it's not acidic anymore. So then in the bottom, The chlorines are balanced, the oxygens are not. Here's an oxygen, so I need to add H2O on the right.
You can't just add OH? No, it wouldn't matter. You've got that.
We're going to follow the rules.
Yeah.
And after you get really comfortable with them, if you want to take shortcuts, you can do that. But I'm not going to do it in front of people. Okay, so that took care of the oxygens, and then I have to take care of the hydrogens. So 2 hydrogens on the left, 2 hydrogens on the right. But this is basic solution. So I need to add 2 OHs. And 2 OHs over here. And this is equal to 2 water molecules.
Cancel one here.
Water on one side.
Okay, so Axel wants to get rid of this guy
Follow me out.
and get rid of one of these guys. I'm fine with that. So one of those would cancel this guy.
Yes.
Yeah.
But do not try to cancel between the 2 half reactions yet. That's not going to be good. Okay, so we've simplified. I'm going to do a little erasing and rewriting here because it's getting kind of ugly. So that was 4 H2O. And this is 2 OH minus. And this mess over here, because of what we canceled on the right, is just 1 H2O. Everybody okay with that?
Yeah.
So the masses are balanced. We got the same number of atoms of each kind on each side, but the charges aren't balanced. So on the top one, what's the total charge on the left side? -5. And on the right side, so we need to add 3 electrons to the product side. So we got -5 on both sides. And in the bottom, we've got -1 here, and then 2 minuses here, so -3.
So you have 2.
So we need to put 2 electrons over here, because we also have this negative charge. So -3 on both sides. So we got 3 electrons in the first half reaction, 2 in the second. And so we need to make that 6 for both. So I'm going to multiply the top reaction by 2. So this 4 becomes an 8. And I'm going to put a 2 in here and a 2 in there. This 4 becomes an 8. And the 3 becomes a 6. The bottom half reaction I'm going to multiply by 3. Isn't this fun? Love this. So that becomes 6. This is 3 and 3 and 3 and 6. Now we add them together. Oops. Resume. When I first started using Docere, I didn't know how to do that, and that was really a bummer, because then I had to write the whole stupid thing over again. I just, there's so many things that can go wrong.
So you can
I don't
get
want
rid of
red.
the electrons immediately, right?
It's all in the trained electrons. That's what electrochemists talk about. I lost my trained electrons. My experiment doesn't work anymore. Trained electrons. Okay, so I'm going to use green. And I've got 6 electrons down here and 6 electrons down there. So those cancel out. Is there anything else I can cancel out?
Hey, water, 3 of waters.
Water. So I've got 3 waters here and 8 there. So if I get rid of 3 of those, then I've got 5 left over there. And then OHs, I've got 6 down here. I'll get rid of those. And then I'll have 2 over here. You could also do that when you actually write the whole thing down, but you just don't have that much space. So 2
Like,
OH minus
sort of a big pile of chips.
aqueous, I know, plus 2 CrOH 4 minus aqueous plus 3 ClO minus aqueous becomes.
All one.
So what you do is you just wrap around and you write the rest of it on the next line. Usually we just kind of start in a little bit. So I've got 2 CrO4, 2 minus aqueous, and I've got 5 H2Os, those are liquid, and I've got 3 Cl minuses. Piece of cheesecake. Yeah. We still have 4 pieces left. Any questions?
Was there any Klondike bars left?
There's 2 Klondike bars left, but I get one. I get one. So there's one up for grabs. The YouTube people are wondering what on earth is going on.
First Klondike equation.